All right, green 7. So we want to show that this is always equal to 0. So step 1, what in the world is this thing, right? Oh, again, the notation's kind of weird. I think the most important thing to realize right off the bat, this is this notation that we kind of don't like. And it's convenient to write down, but it's not clear what the vector field is that we're dealing with here. So I like to observe that this is the same as, so we're trying to figure out if that's equal to 0. But let's just rewrite what this expression is. This is, I've got to figure out what vector field is dotting with the dx vector to give me that thing. Well, okay, clearly this is 0, and this is f of y. Right? So this is the kind of, this takes a coordinate line integral and rewrites it as a vector line integral. Namely, I'm going to call that f. This is exactly what the dx vector is. And so that means that p is equal to 0 and q is equal to f of y. So there's my vector field pq. Is that cool? Is everybody happy? So this is kind of, there are several problems along these lines, what I've done here in 513, or I believe it's 513. Yeah. The coordinate line integrals and surface integrals section. Okay, so let's see here. Now this path C is the boundary of a region, so let me rewrite this as integral over the boundary of some two-dimensional region. And I've got f dot dx, and Green's theorem tells me that this is the double integral over that solid two-dimensional region of green f, dA. Now, what is green f? Well, it's dq dx minus dp dy. Let's write that down. It's going to be the partial with respect to x of q being f of y. So there's dq dx minus dp dy. What's p? Well, p is just 0. And what I've got here then is that I'm doing a double integral of, well, I claim 0 because I'm taking an x partial of something that only depends on y. So this partial derivative is 0. Here I'm taking a partial of 0. That's definitely 0. I have integral 0 dA, and that's equal to 0 as desired. That make sense? Everybody happy?